Josh Stewart. I'm Trevor Johnson. I'm Chris Lasser, and today we're going to be going over our project one for Physics 212. Okay, so the problem that we're given is we're needing to find the speed of the cue ball after we hit it with the cue. And we're given the force done on the ball from the cue, the radius of the ball, and then the time and the mass. So we need to find where the cue is going to hit the ball. So we need the height, and once we have the height, then we can figure out how fast the ball is going just using rotational motion. And we're gonna have to make some assumptions to figure this out. And to do that is we're saying that there is no friction when we hit the ball, and then we're saying that the ball is heading in the negative x direction. So that's part one, and then for part two, we're gonna have to find the rotational and translational motion since we need to find when the ball starts to rotate and not just slide after being hit from the cue in the middle of the ball. And then after the ball is struck, we are assuming that there is no friction when the ball is being hit as well. And then we're going to find the how far the ball travels. Yeah, so I'm going to be going over the first two questions, the first part and the first two questions. So what we're trying to find out of this is we're trying to find the height at which the pool cue is hitting the ball, and then we're trying to find the speed at which the ball is moving without skidding, so just with static friction. However, as we said earlier, we're ignoring friction at the point of contact and when we're hitting it. So we won't be talking, so we pretty much ignore it, and we'll show that in here as well. So to start out with, we're going to find our transitional equations. So we're the sum of the forces for the x axis. We basically have the force applied, so Fs, minus the force of static friction, which we have here. So we have the force applied going that way, and then we have the static friction going that way, is equal to mass times acceleration. Now, because we know that we can kind of ignore static friction, we can just get rid of that and call it zero. So that we can say that our applied force is just mass times acceleration, which will come in a little later on. Now, in our y position, this one's pretty easy because the only forces that are acting against each other are the normal force of gravity. So we know that the acceleration is going to be zero in the y direction. So just the normal force from the table is going to be equal to the force of gravity. So that one's pretty simple. For this problem, our moment of inertia is going to be the 2/5 mr squared. We found that using the moment of inertia tables. So now let's start out with trying to find the height. So the height at which we're going to hit it, we're going to use torque to find this. So we have the sum of the torque is equal to is going to be the force applied multiplied by the height added to the force of static friction multiplied by the radius is equal to the moment of inertia multiplied by angular or rotational acceleration. So then if we plug in all of our equations for this, we know this is going to be the same. So force of static, the force applied multiplied by the height is going to be equal to the coefficient of static friction, mass times gravity times the radius, and that's just the static friction equation. Is going to be equal to our moment of inertia. We'll plug that in here. And then for the rotational acceleration, we're going to plug in acceleration divided by the radius. And then what we can do from here is we know what we're going to ignore because we know that at this point of contact, there isn't going to be any static friction. So we can automatically just get rid of that because we're told we can ignore it. So we're going to ignore it. Then right here, we know that this is a radius squared divided by the radius. So let's just get rid of it. So we can get rid of a radius there and get rid of the squared. So we're just going to have one radius. So then Right here, putting it down, we have our applied force multiplied by the radius, or the height, sorry, is going to be equal to 2/5 multiplied by mass times acceleration, which we have up there, multiplied by the radius. So we know that we have mass times acceleration, and we know we have that right here as well. So we can just plug these in for one another, and then we can get that the force applied multiplied by the height is equal to 2/5 multiplied by the force applied multiplied by radius. Now with that, we can just completely get rid of the force applied. So then with this, we know that the height is equal to 2/5 times the radius. And this just kind of makes sense when we're doing it. We don't want it, it's not outlandish. It just kind of it could be true. Though if we're given numbers, we don't really have numbers, so we can't really test this out. But then the second part is trying to find the speed of the ball without skidding, just rotating. So we know that the acceleration is going to be equal to the force applied by the pull Q divided by the mass of the object. So we know that the acceleration is the force applied divided by mass. It's pretty simple. Then we're going to find that our speed or velocity is going to be equal to our acceleration multiplied by our final known time, which is delta t. So that is our speed, and then that is our height.
Okay, so for part two of the project, the point of contact between the cue and the ball moves to the middle of the ball. So instead of just rotating, the ball is also going to be sliding for a brief period and then just starting to rotate. Um, so that's what we're trying to find is the translational rotational motion after this contact, and then the distance that the ball will slide before it starts rotating. So to find the translational motion, we use the kinetic friction force, and we set that equal to mass times acceleration. And notice it's in the negative direction, and that's just because we're hitting the ball to the left, and that's an assumption we made because um, we're rotating the ball to the left in the first part, and that's all just rotational motion, so it's in the positive direction, but for translational, that'll be negative. Um, so to find this, we just divide both sides by m, and we get that the acceleration will be equal to negative force of kinetic friction, which is mu k times gravity. So that's the translational motion. And then we use torque to find the rotational motion. So we set the force of kinetic friction times r equal to the inertia times the angular acceleration. So using 2/5 mr squared as our moment of inertia from the tables we found online, we set that equal to the force of kinetic friction times the radius. And we're able to cancel out the mass and the radius on both sides. So we got that the mu k gravity equals 2/5 r times angular acceleration, and then dividing both sides by 2/5 r, we get that the angular acceleration will be um, 5 mu k g over 2r. So that's our rotational motion. And then for the second part of this problem, we find how far the ball will slide before it starts rotating. And because we know that the rotational motion is going down and the translational motion is going up, the point at which they meet is where the ball will start rotating after it slides for a brief period.
Oh, sense making. So for part one, we've got the height, which is just going to be in meters. This makes sense because we have 2/5 of the radius in the positive y direction, which is in this location. Then we have speed. So we have for the force, we got mass times meters over second squared, and then this cancels out with the mass already being divided. Then we're left with mass over seconds squared times seconds. So these cancel, leaving mass over seconds. And part two, we have translational rotation, and this is going to be mu is unitless. And then it just leaves gravity, which is meters over seconds squared, which is acceleration. And then we have for rotational, we have mu as unitless once again. Then we have gravity, which is meters over seconds squared. And then we have down here meters over seconds squared over meters. Whoops. which then is being multiplied up here, leaving meters squared over seconds squared. That all makes sense. And then, so the similarities, this problem is really similar to a problem that we did on one of the homeworks where we have two different spools, and one's going to be a fixed location and a non-fixed location. And each one of these spools are going up this ramp here. And we figure out that the spool without the fixed location has both translational and rotational um, motion, and then the fixed is only going to have the translational. Difference is we didn't really need to find translation or rotational for each of these problems. We just needed to figure out when these spools cross the line, so we just need to find the distance. That's all was needed.